Now, in reality, what really happens is that this loudness, the amount of air molecule going up and down, is going to change. They're going to reduce, and amount of amplitude here is kind of dies out. This is well explained and introduced in the differential equation, and this part of the force is called the damping force. It's going to call right and damping force. So here could be the frictions between the air molecules, and if it's really the spring mass system, and then you can the mass itself a lot bigger object than air molecule, and we have air resistance and things like that. There is some natural part of the nature is try to reduce this motion and dies out. So that's the damping force. For example, for a guitar string, there has very, very strong tension to create the sound. If you lift up the guitar string in here, and you certainly feel this force to return to this one, there's a tension. So as you release it, that position of a string will go up and down and very quickly, but the tension is the damping force to reduce it down, and within a matter of second it almost does not move anymore. So that will be the damping force for the string of the stringed instrument. It's really fun to study mathematically how this force is added when you calculate the net force, and mathematically how this one come up as a factor of this this position function. So we will skip that complicated mathematical deduction and just give you an answer to the typical damped harmonic motion. Harmonic means its damping force is already there, but it's still, we have a nice perception of this frequency, and that's the magic. And then an early part of the video I have already explained there is some motion, although it kind of dies out. The frequency, the time interval that takes go back and forth, is when it was loud and it was softer, the time period exactly the same, hence creates the same frequency in the beginning at the end, perceived as a nice sound. So here's how the typical one looks like. So here's maybe different. I think I called it in my Mathematica program a third function, so if not, it might be the same. So here's the sine. It's still there, the formula. When after you deduce this thing, the sine shows up, but this damping force shows up here in the position function as follows. There's exponential kicks in and c times t. So this is a frequency, and this c is some constant that is relative to, pertinent to, the material and the situation. So if the sound dies out really quickly, then it might be in this form. And if it is in this form, we call it the damped harmonic motion. So the damped part is there's this factor kicks in and reduce this amplitude quickly, and we still use this word harmonic here because of the frequency and a period still untouched. That's the amazing part. So if you sketch this typical thing, then we have the sine phenomena. The function of sine crosses x-axis in regular period, and that's exactly again a phenomenon of keeping the same frequency all the time. Even with this damping force, this period and frequency is still kept, but this is because of this negative c part right here. The amplitude, which is governed by what is multiplied in front of sine, is quickly decreased. So you have like upper envelope and lower envelope here, and the sine function starts and trapped in between this this thing. So the graph of this function looked like this. Again, the miracle here is this crossing it here is exactly the same period. If that happens, it's damped harmonic motion, and some of the simple physical principle you write down, such as Hooke's law and air drag, air resistance, simple principle about air resistance, something like that. With this much of information, you can sometimes deduce that the motion that doesn't seem like have a harmonic phenomenon anymore and still have this harmonic phenomenon. And this is a miracle, allows us to enjoy music from the musical instrument. Now I'd like to do that in Mathematica, and here's a really interesting part with the Mathematica, and no parts of the physics and the mathematics books say anything more than what the damping constant does. So here's something I'd like to claim an interesting part. So here's a Mathematica input of a damping part here. So I kept the same frequency here and the higher pitch. So I multiplied this damping factor, so it quickly dies out. So here in the bottom, I have prepared right here. This is the 440 with the damping force, or 1.5 higher than that, I'm not sure. But so I'm going to play it here, and the only difference between this one and the machine like sounded before, is damped or not. So far what we understood is that this amplitude goes down really quickly. The difference is as simple as that. But our perception here creates a slightly different sound quality. I want you to hear that. So here's with the damping constant. So let me play that again. One more time. One more time. So if you compare that with the simple harmonic motion before here with the same sound all the way, it's very, very different. The damping phenomenon itself kind of created some sort of texture into the sound to me. So it is this damping, how the sounds are damped, is actually an important part of the timbre and sound quality that we perceive. Already this one created some sort of piano sound, piano-like a quality of the sound. So the damping part, I think, is important quality of the sound of the piano. And the guitar. Violin, as the way that we are bowing the string, is try to keep the sound as the amplitude as same as possible, so it's a slightly different phenomenon. So one more experiment I did with the computer is that these two things are the damped sound, Y3 and Y4. You have a damping factor. So I added this to perfect fifth interval, and I added some sustained notes. This Y1 is not losing its amplitude, but its amplitude is kind of kept down. So like a violinist play certain sound at the beginning, very loud, two notes, like double stop of two notes, very loud, and it quickly kind of switching the bow and loses loudness quickly, and then kind of hold on to the one note with a fairly small amplitude and loudness in here. So that is represented here with most of the sound dies out, but there's a certain part and maintained with a same strength. So here's how it sounds like. So again, just with this damping part, not really changing than how things are moving, already creates a slightly different experience of the sound, not just the sound. I think it's an important part of sound perception. So my last word is that this damping force everywhere in the nature, and in this miracle with the mathematical differential equation, still allows us to have this fine frequency still there, is our everyday experience of from the musical instrument. So behind it is a miracle from differential equation. Thanks.